Hello, Professor. After our class, I would like to ask the questions, the problem in our homework. Are you available?
Of course, I'm available.
Okay, thank you.
Okay, so let's start then. All right. So do you have any questions in general? So our first midterm is next week, right? I think I'm right. Correct me if I'm wrong. So what we'll do is, I think the time for the midterm is something like 1 hour 20 minutes, right? So I'll decide on that, but something along that line. Or like, basically I want to be half the class. Okay. So because we have a small class, I think what basically I'll do is you just take the exam within the class, right? So I think what I'll do is, like, first half is lecture as usual. Second half is exam. Oops, sorry. Okay, where you basically just turn on your webcam. Okay, you just turn on your camera and take the exam within the class. Okay. So write your exam on your papers and then just upload it onto Canvas. So you turn on your webcam so I can proctor you, right? What I'll do is I will try to break you into individual room, so that, I mean, if there's a concern about privacy, you won't see each other. Okay, so you will each be in a different breakout room. Okay. I'll write more details about what I expect of the exam. But so basically the materials is going to be capped by today's lecture. All right. So mostly it's going to be like homework, like questions about mathematics, computation, Black-Scholes, Ito's formula, Ito calculus, Black-Scholes formula, that kind of thing. You can bring 1 page of note. Okay, one-sided. Content unlimited. You can write whatever you want on it. But on the other hand, I don't want people to write like, really small stuff and then just pack the whole page with information. Okay. So I would do something like, basically I require, you to have like, I don't know, at least 11, size 11 font. .5, is like, it's double space or something, but okay. I don't know how to say this. Maybe single space is fine. Yeah, you spell that right. Single spacing, single spacing or something. Anyway, the point is that please do not, like, pack your whole note with like, like tiny information. That's just ridiculous. Okay, so don't write the whole, don't put the whole class. lecture on it. Okay, because you will have to turn in your own page of notes, and if I would judge if somehow I feel like you write too much content on it, it looks weird, then you may lose score on it. All right, and I hope you know what I'm talking about.
So our notes are also going to be graded. So like,
sorry, Don,
I mean, they're mostly typed.
No, you don't have to. So that's why, I mean, you can write it, right? I just don't know how to describe, I need to have some rules, right? So you can write it, right? And if you write it reasonably like this, I have nothing against you. You know,
Okay.
I mean, but I'm sure you have seen people who wrote like tiny. I wish I have a sample to show you. It's just amazing. So, right, you can just do the most natural thing. You can prepare your notes with handwritten stuff, right? And if you want, you can send me a copy of that and ask if it's okay. Okay, I'll be happy to tell you. Okay, like that looks fine, for example. Okay, so basically the point is I don't require you to memorize Black-Scholes formula kind of stuff. You can put it down on paper, Ito's formula, right? But preferably you should memorize it. Nothing out of the ordinary. So the class, again, the exam is designed to mimic the class homework and lecture and discussion, that kind of thing. So you get most questions will center around the math, right? But you may also get coding question, okay? But let me tell you how I plan the coding question. Of course, you have no access to Python. So I'm not going to ask you to code in Python or anything like that, but you would need to write down pseudocode. Does everyone understand what pseudocode means? So basically, you just tell me, I will generate this thing. Like say I generate like random normals. With this variance, I will add them. I would take the average, that kind of thing, right? So you don't have to write down precisely the command, but you will tell me the ideas of how to do this kind of things. For example, I say, write down the pseudocode to demonstrate that the quadratic variation of the Brownian motion is t, right? Then you write down, right, what the idea is. Of course, there's something that has to be precise. For example, like you would take the function, you would need to generate Brownian motion somehow, right? You need to basically divide the interval from 0 to 1 into so many subintervals. Those things need to be a little bit more precise, but the exact command you use won't be required. As long as you say, I divide the interval into subintervals, that kind of thing. I don't care how it's done on Python. Is that okay? So pseudocode. Of course, right, the grading of this will be a little bit not as strict because it's pseudocode, but I would judge, right, whether or not what you wrote down convinced me that you understand, right, what you're doing or not. Also, like kind of finance related question possible. Not sure about this, but again, here's a graph of the Greek. Tell me what do you think about the behavior of this financial product, right? Here's a like a spread, right? How do you think this spread is doing? What purpose does it do? That kind of thing. The bull spread, the bear spread, right? Again, similar to the homework, right? But require you to again put that into content on the exam. Is that okay? So very much similar to the spirit of what we do on the homework, right? Testing how you understand these materials, how you kind of put this down into papers. That's all. Any question? Okay, so yep. So you're required to take the exam in person, all right, on the second half of the class next time. If for some reason you have some commitment or something, you cannot make it to the exam, please tell me beforehand, all right? Let me know before the exam that somehow you cannot make it for some reason. Okay, otherwise I would expect you to be there during the second half of the class. Any question about this? Okay, so then let's start with our lecture then. So last time, right, we talked about the change of measure, right, or Gasanov theorem. Right. There are many levels to the Gasanov theorem. Okay. At the more basic level, it tells you that there is, right, the most basically, right, most basically, in terms of finance, right, it tells you that if you start out from the physical setup, right, of Black-Scholes, and you want to convert it to the risk neutral measure, right, risk neutral world, then it tells you that there is a change of measure kernel, right, ZT, yes, so that, right, so what is the relation between this guy and this guy, right? That's what you should be able to figure out just from looking at this. The relation is W tilde. So okay, right. First of all, what does ZT do, right? ZT, a change of measure kernel. You should know what this means, right? That means that the new measure, right, is defined by the old one times ZT. That's all. Like that, right? So the effect of Z, right, is that the W tilde, which is W, right, plus mu minus R over sigma times T, is a Brownian motion under P tilde, right? That's the effect. So in other words, it guarantees us that, right, for each term like this, there is a Z that corresponds to it that would guarantee, right, that the Brownian motion with drift is, sorry, the Brownian motion with drift, right? So the Brownian motion with drift definitely would not be a Brownian motion under P, right? So you need to change the measure. And with the change of measure, right, this guy, it kind of takes a drift away, if you will, right? Then this guy will be a Brownian motion under P tilde. Is that okay? It is a little bit complex in terms of all the information it packs together, right? But what you want to know, right, what you want to pay attention to is this structure right here, right? How the change of measure is constructed and what object it changed, all right? The details you can just track from the proof, for example, but this is important. Any question on this? So let me tell you, right? I mean, Gasanov, I would admit that this is one of the more theoretical results you see in this, lecture so far, right? I tend to be more practical. But let me tell you, right, that actually these kind of things show up in very practical places. Well, it shows up on interview. I'll show you how. But it also shows up in, the content that we'll do later, which is the foreign exchange. Okay. When you do foreign exchange, by nature, you are forced to use change of measure kernel, okay? Because you will need to price stuff in the foreign currency on the foreign money market, all right? So for that reason, you have to use the change of measure kernel. you have to switch to the foreign money market to price the product. Okay, so there, as we'll go to that chapter, you see that you just have to use it naturally. But even closer to home, all right, let me show you how this this stuff shows up, like say on an interview. So it has to do with something like this, right? Black-Scholes formula. I think by now, right, all of us are very familiar with Black-Scholes formula. So it has to do with a call option. And it tells us, right, that V0 is S0 ND plus minus K e to minus RT ND minus, right? So first, I guess you go on interview, people expected you memorize this. Now then the interviewer would ask, okay, tell me the meaning of ND plus and ND minus. Tell me the meaning of ND plus and ND minus. What would you say to that? What are the meaning of these two terms? At least you should see something somewhere already about this, right? At least you should be able to say something. Anyone? For example, what's ND plus? Or at least have you, where do you see ND plus? Yes, Don? Are you trying to say something? So you should have seen ND plus in the delta, right, of the call option. So ND plus is the delta of the call option, right? So if you want to, you can say ND plus is the delta of the call option, which is okay, right? That's one meaning, right? But here, I guess they want to look at and first of all, right? What are these objects? These objects are probabilities, right? So what are the probabilities of? What kind of event are they giving you probabilities of? Don, I'm not sure you're trying to say something. I just don't hear anything from you. You can type in the chat if you want, but all right. So how would you answer this question? Well, you answer this question by going back to how you find V0. Okay. So V0 by risk neutral pricing. Okay, let's see what. Yes, very good. Exactly. But so you're getting somewhere. Now the interviewer would want you to say, okay, which one is which? Oh, that's fine. Which one is which, right? That's good, but you're giving too many possibilities, right? Notice that we have two terms, and you say in or out of money. Okay, which one is which one? So D, you're saying that D plus, ND plus is probability the option expire in the money. And ND minus, right? Okay. Out of the money. All right, fine. Now you're using finance term, which is very good, right? Let's translate it to the math here. What do we mean by expire in the money and out of the money? Well, I hope that what you mean is this. PVT bigger than K, right? Because we're talking about call option here. And this is P, sorry, not VT, right? VT positive or ST bigger than K. ST less than equal to K. Is that fair? That's what you're trying to say, right? Okay, not bad. But then the interviewer would ask, or you would be expected to say something like, well, you are aware that there are more than one probabilities going on here, right? There's a physical probability and there's a risk neutral one. Which one are you referring to? Right? I mean, it's only fair that there are more than one probabilities going on here. So which one? Physical, right? I mean, there's a physical. I would say that's a wrong guess. That's not a good guess, even if you want to guess, right? If you're not aware of it. Why is it physical? Well, why should it not be physical? Because this is lifted straight out of the Black-Scholes formula. Yes, it's lifted straight out of Black-Scholes formula. And Black-Scholes formula, you know, it comes from risk neutral pricing. I would be very suspicious if somehow the physical probability shows up. Does that make sense? Without even like trying to justify things. If you just judge from the context, you should not guess it comes from physical probability, right? In other words, if you want to guess, and now I'm just putting words in Dom's, kind of statements here, is that it's reasonable that you should say it's risk neutral. Are you convinced? Or if you want to go with physical, it's fine too. Then the interviewer would push why you think it's physical, right? So, right. So these are things that, again, I'm just saying, right, that you would need to demonstrate, right, to on a Black-Scholes kind of question or interview. But that's not the end of the story, all right? That's not the end of the story. Is it okay so far? Then they would ask, okay, fine. This is your guess. Explain to me why you guessed that way. Or bluntly speaking, right now I'm the new year, I'm telling you, that's not correct. That's wrong. Okay, that's somewhere near the truth, but that's not the answer. All right, and the interviewer, for all you know, just staring at the answer sheet somewhere. So why is it wrong? Right. So now they poke deeper, right, into your understanding of the Black-Scholes formula. Okay, so that's closer to truth, but that's not right. Okay, so there you need to see, right, different contexts of the Black-Scholes, which is, by the way, all that you've known already. You just have to put it together. So V0, right, by risk neutral pricing is E tilde of E to minus RT ST minus K plus. Do you agree? That's risk neutral pricing. How do you break it down so that it looks like this? Can you see a way? How do you relate this and this? That's actually the question, right? Well, you see that no, yes and no, right? That's fair, but probabilities, not by discounting Kashif, because discounting just gets you back to S0, right? It doesn't help you. Remember, the difficulty is the plus right here. Okay. Do you see any plus in here? By the way, right, this plus and this plus are very different things, right? This is the max between this and 0. Right? This is just a plus notation that says, it's a term. So you can interpret Don, but you have to be more precise, right? Because expectation doesn't match probability naturally. Or to be blunt, right here you have one term, here you have two terms. How do you interpret to match? Yes. Again, right, I am trying to help you to see here, all of you actually, that the number one, not number one of the distinguishing marks between, let's say, a successful candidate and a candidate who don't, is not quite successful for an interview is, I guess everyone should be able to say something about Black-Scholes. If you cannot, then I guess you just don't make it to the interview. But a successful candidate can say precisely, right, or argue precisely.
Professor,
Yeah.
I wonder why. You draw this signal between the ND plus and ND minus.
Right here. You're asking me
yes.
why did I do this? Because the answer
Yes.
is wrong. I claim the answer is wrong.
Why?
It's not. Yeah. I'm trying to explain now. That's what I'm trying to explain now.
Okay.
I was asking if you know why. If you know why, feel free. But I'm telling you that this answer is not right. It's not precise. Okay. So yeah, right. So I'm just trying to explain that, like, being precise, right, is that, I don't know, 10% push that gets you to your job, right? And I'm not kidding about this, right? I mean, as a student and as human, I know we just want to know roughly. Yeah, that sounds like the idea. Agree in usual day, okay? But on an interview, if everyone can say something, right, the one who can say it most precisely will get the job. All right, that's all I can say. So here, right, like what Don said, right, it sounds right. You want to break it down, but how? The how is by the indicator function. Okay, remember, and I don't know how often you will see this, but I did say, right, when you want to convert from expectation to probability, indicator function, okay, is the tool. One if A happens, zero if not. Okay, so exactly what Don was suggesting, you would break this down. You would use indicator function to get rid of the maximum. Yes, because it's going to be this if this is true, be zero if this is not true. So indicator function exactly does the job. Okay. Now, this being a function, right, you can just separate it into two terms. Is that okay? Now, after we do this, all right, now Don, right, matching probability, can you tell me if you see something? Where's the Black-Scholes, right? Right here, right? Matching this and this. Do you see anything? Well, again, right, this is S0 ND plus minus K e to minus RT ND minus, right? Supposedly, because that's Black-Scholes. You can tell. Look at this too. What can you tell me? Yeah. What can you tell me? What can you tell me? I hope you can tell me that ND minus is probability. Yeah, it's not independent, but it's a constant, right? You can factor it out. So ND minus is probability, right? So do you see why I say this is wrong? Right, Sharon, you see that, right? Is this?
Yes, I saw that.
Right, so that's wrong, okay? But again, right, I understand. I understand that when someone says this, they are expecting something. But right, you see the reality is this is this. So you did say a wrong statement, right? But why do you say this wrong statement? I would say because you're not very good, Don, right? So now your mind's thinking. Except, is that true? Is that true that this is this? Right? The math doesn't say that. Yes? Right, exactly. No, honestly, no. So Sharon, you want to say something?
It's not true since since n must be a positive number.
You mean what Don said is not true? Is that what you're saying?
ND minus must be a positive number.
So what is not true? What I'm writing here is not true?
And don't type that ND plus is a negative one.
No. She doesn't mean
It's a
minus.
negative number.
She doesn't mean minus. She means tilde. She could not write p tilde. So she write tilde. She is not. It's not minus.
Oh.
Yeah, she write tilde.
Oh.
Her mistake though is she writes a less than, which is a good guess because one is plus, the other one should be bigger, the one should be less. But I was pointing out it should not be right because here it's still bigger. So no, she meant tilde, right? So she's fine. She meant less than. That's where it's wrong because I don't see why it's less, right? It's bigger, right? So her guess is natural. Oh no! Do not be sorry. Okay, I'm not sure you just say it politely or not, but don't. Okay, please, just guess. Okay, I'm trying to help you out seeing things here, so feel free to guess. But it's a very good guess. All right, I have to say that. But no, it's not. It's not. It is a natural guess, right? Don't be afraid to guess. But after you guess, you should be able to judge whether your guess makes sense, right? That can also be helpful on an interview. Okay, you should be able to talk to the interviewer, right? You're on the phone, I suppose. So if you keep silence for a long time, then it's awkward, right? So you could guess, like I would say Don would probably guess like, oh, is it then it's out of the money? But then your brain should race right away, right? To say, well, but wait a minute, that doesn't make sense because this is still bigger. Okay. Then the interviewer would appreciate that you're thinking. All right. I think making a bad guess is not bad in of itself, as long as you recognize it's a bad guess right away. Is that okay? I think that's my advice. That's my take on it. Anyway, right? But so let's stare at this for a little bit more, right? So are we okay? So ND minus, okay, is famous. ND minus is famous for being probability, the risk neutral probability that the option is expires in the money. Okay, that is common knowledge. The not so common knowledge is this term actually. Okay, but then right. So look at this a little bit, right? Do you see that this is not exactly a probability? That's the end of the story. This is not exactly a probability. In Don's guess, right, or what Don was saying before, this is a constant, so you can factor it out. So you can leave you're left with the indicator function. So you're fine with that. But here, right, is a random variable here. All right. So how in the world does that become that? Anyone has a guess? So let me write down something, right? So obviously the matchup, right, is this now. Right? Let me rewrite like this. Not sure if it helps. You recognize what this is here? It's not easy, but this is a change of measure kernel. A change of measure kernel. All right. Why? Remember, right? I did not state the condition of the Gursanov, right, up there. But from your homework, I hope you remember something like this. That ZT, right, whatever you choose for your change of measure kernel, should be a positive martingale whose expectation is 1. Positive because you want to preserve probability, should be positive. 1 because the total probability is 1. Do you remember one of the fundamental results about the discounted stock price? The discounted stock price is a martingale, right? Under the risk neutral probability, and it's positive because stock price is positive, is a positive martingale, right? Of course, expectation of this guy is not 1. So it cannot be used as a change of measure kernel. But of course, right, if you divide by a constant, then that's still, right, a martingale. A martingale divided by a constant, right? S0 is a constant. And expectation of this guy obviously is 1. So what this is yet another change of measure, right? You change from physical to risk neutral. Then you change measure from risk neutral to another. And this one will have a technical term, right? We haven't introduced it. It is called the measure, the measure using S as a numeraire, okay? So basically, ND plus is a probability using S as numeraire of the option expiring in the money. That's what it is. All right. So I expect at this level, right, that you probably have no idea what this is. And frankly speaking, you know, it's not something easy to see. But what you could see and what you can already see is this is a change of measure kernel. That's all I'm trying to say. All right. That this is still a probability, but it's not a probability under risk neutral. It's a probability under another measure where you use the stock price, discounted stock price, as the change of measure kernel. Okay. So that's the interpretation of ND plus, if you want to interpret it as a probability. Of course, ND plus straightforwardly is the delta of a call option. I find that very natural. But if they want a probability statement out of it, this is a probability statement. So both of them are involved with this, the option expiring in the money. Okay, but the measure is very different. One is risk neutral, one is the measure using S as a numeraire. Here's a numeraire. Okay, we'll talk about this later. All right. Yeah. And true story, right? This is an interview question I got from Goldman Sachs. So I'm not sure how relevant that is, but they did ask me this question. Okay. And I also did get stuck here. I know ND minus right away. I don't know ND plus, right? But then I did kind of saw that it was, you know, change of measure kernel. Anyway, after having taught this class at that time, I taught this class at that time too. But, you know, again, right, practical experience and theoretical knowledge doesn't necessarily connect. But I did get this question, all right? So it's not like, you know, interview for some reason don't drive around this area. But so I just want to bring this up. So to show you that, right, change of measure is a practical concept that could come up. That's all, right? Even in something as simple for you as Black-Scholes. Any question? All right. So now that is what I want to say about change of measure kernel. We'll go back to this, okay, again and again and again. Now let's take some time away to now discuss the Greeks, okay? The Greeks. So of course, I never really officially lecture about the Greeks. I've let you play around with it, at more or less the formulaic level on your homework and in your discussion session. So the Greeks, right, at the heart of it is pretty straightforward. Basically, the concept is that you have an option, right? You have V, okay? Option value, right? It's always a function of all the parameters underlying the model. So all parameters underlying the model, right? And this is the most general way you can think of the Greeks. Basically, because here we don't say what model it is, all right? It can be any model. It can be any model. It doesn't have to be Black-Scholes. Of course, a model has parameters. So a option price, or however you price it, will be a function of the parameters. That's it. Okay. Now, if you want to specialize to the Black-Scholes, then V will be a function of what, right? It'll be a function of, R, sigma, the current stock price, right? K and T is 5 parameters, right? So you being a function of anything, right? And of course, here there's like this mathematical requirement that we ignore, that it needs to be smooth enough to differentiate in these parameters. But basically, at least at the waving hand level, you could take the derivative with respect to any parameters, right? Like this. And this guy, by the way, right, has a minus sign in front. Okay. So, right, when someone asks, why are you interested in these, right? So this is, of course, right, the delta, the gamma, the vega, and the theta, I think, right? You say, well, they give me an idea of the sensitivity, right, of my option price with respect to the underlying parameters. Okay. Someone asks, okay, again, why do you care? I hope you see, right, that is because these guys, right, are not constants in real life, right? Obviously, stock price will change. So that's the number one thing you care about, right? I mean, at any moment, your stock price will move from one spot to another. So if your stock price moves, you want to know how your option price moves. But not only that, the volatility, right? It feels pretty funny that you say the volatility is a constant here in the Black-Scholes model, but here you take the derivative with respect to volatility as if you're expecting volatility is going to change. But obviously, yes, right, the volatility will change. So that that tells you like different levels of assumption on the Black-Scholes don't mix with each other, right? And maybe someone will ask you about that, meaning, so how do you reconcile these two facts? But anyway, right, the fact of life is volatility change, right, in the market. So you also want to know if volatility changes, right, how would that affect the option price? Okay. Same with interest rate. This is time to maturity, right? And again, time keeps collapsing, right? As time moves on, your option price will have less and less time to maturity. So you want to, right? So this guy actually is a decreasing function, you see, right? This guy is a decreasing function as time goes on, right? So most people don't do T, they do tau to distinguish, right? Because for us, big T is time at maturity, like June 10th or something, right? Tau is time to maturity, meaning you have 2 months left, 1 month left, right? T is a moment in time. Tau is the time interval left. In other words, tau is T minus T, T minus T, where T is the current time, right? So that's why it keeps decreasing. So that's why, when you take if you look on Wikipedia, right, they put a minus sign in front. All right. So we'll talk about this a little bit, okay, in connection with the math, of course. I want to discuss something non-trivial. I will leave something pretty straightforward for you to figure out. But one thing that I would want to mention, right, is you are aware, I hope you're aware, that these guys are super practical, all right, super practical. A trader, right, which I guess, anyone who studied quant finance would dream to be a trader or something. One of their jobs, right? You might think that the trader job is to make money. Not necessarily, okay? Maybe that's the implied, or whatever consequence. But their task, as explicitly stated, would be, I won't be surprised, would be to manage the delta and the gamma of their portfolio. To be blunt, right? One of their tasks is to manage the delta and the gamma of their portfolio. Now, of course, right, the delta and the gamma of the portfolios will be super complicated, right? It's not just going to be straightforward formula from a Black-Scholes, because the portfolio definitely does not just have call options, right? But like even at that sophisticated level of a job, right? What they do is to play around with the Greeks and make sure, right, it falls within some tolerance level that the company set. Okay. So that's why these guys are, things that you keep hearing all the time. So obviously, well, I mean, obviously or not, one of our alumni and my friend, he's a trader now, and he told me he does exotic option. Okay, and he told me that right recently with the the GameStop thing, right? I'm sure you have heard of it, right? How the people who trade GameStop drives the whole market crazy, right? So there, actually, he said, right, his his portfolio is out of whack, and he has to spend a lot of time trying to fix the Vega of his portfolio. All right, so it's fascinating. I did not quite get the whole point of his what he told me, but what he said was right that because people who trade GameStop kind of buy a lot of out of the money call option for like really cheap, they end up somehow messing the Vega of the volatility of the underlying market, and then that in turn affect what he does, and then so he was dealing with that a lot during that time a couple weeks ago. Okay, so all right. So what do we want to say about right these guys? So obviously the number one thing you want to know, right, is for the call option, right, call or put, right, vanilla. These guys have explicit formula, right, that you have already used again and again and again. Okay, I won't quote them. Now, of course, for things like synthetic spread, like the butterfly, the iron, condor, the bull, the bear, they are synthetic from the call vanilla call vanilla put synthesized. So therefore, you can also have explicit formula for them, right? I mean, again, the homework makes it clear. What may not be clear, right, or what actually won't happen is the area of exotic option, right? Exotic option, American option, for example, or any other kind you have, or a different model. So what do I mean by this, right? Exotic option, which is an area we will talk about right soon, basically does not have explicit pricing formula, does not necessarily have explicit pricing formula. So therefore, the call and put, the exotic option does not have explicit formula. So let me just say, right, does not necessarily have like a Black-Scholes type of formula. Okay, so all these I list don't have Black-Scholes type of formula. So, but the Greeks, right, still make sense with these options. Okay, the Greeks still make sense here. You understand what I mean, right? Just because you don't have a formula for the price of these options doesn't mean that the idea of the Greek does not make sense. Why? Because ultimately they are still built upon the Black-Scholes model, right? All of these, what I mean, right, is exotic option on a Black-Scholes stock, meaning this. Okay, except for the last one where it's a different model. But we'll talk about this later. But say exotic option and American option, that's still built upon the Black-Scholes model. So whatever price you come up with is still a function of R, sigma, maybe not K because maybe there's no strike, but some other stuff, function of S naught, right? So the notion of gamma, delta, and vega still makes sense to them. But the question is, right, how do you even get to the level of the Greeks because there's no explicit formula? Well, the answer is, right, that's exactly where your numerical method comes into place. Numerical method, right? And the numerical methods can be pretty crude. Like, for example, right, you have seen that the delta of a call option is approximately V0, right, at level S, level S plus something minus V0 at the level S divided by epsilon, right? Okay, so this is a difference quotient. If somehow you have a way to simulate this, let's say by Monte Carlo, right? If you have a numerical way to simulate the option price, by the way, right, that's what I mean. You don't have a formula. So that's why now simulation becomes important, because with simulation, right, you can get to an approximate numerical value of this option without knowing what the formula is, right? Then you simulate for a stop price that's slightly higher, you simulate for a stop price that is at the level you want, take the difference, divide by epsilon, right? And you see, this is purely a numerical approach. And I do imagine and I do believe, and I think this is what happens in industry, right? They do so many products that is non-standard that, no formula is readily available. Yes. So I do believe that quants who work on explicit formula for that. But the most practical work would be what? I don't care for the formula, right? Here's a product that a client wants. Can you build some sort of approximation that is precisely enough, right? That would allow me to know what the delta and the gamma is of my position for the client, so I can charge them. Yes, or I can just, or the trader, right? Imagine the trader ask you as a quant to approximate, the delta and the gamma of his current portfolio. Okay. You see, the challenge is not the idea, right? The trader is not, is definitely smart. They know this idea too. But the challenge, right, is somehow to make this precise. Because as I pointed out to you, right, the Monte Carlo is pretty crude. If you just apply it at the level that we do in this class, the conversion is very slow, the error is high. So how do you make these conversions fast and the error small? Also, how do you make this approximation better, right? So those are the practical areas that I'm not teaching you, and frankly speaking, I'm not an expert of either, but right, you can pick up in some other courses, all right? But what I'm trying to say here is only that the Greeks, right, are relevant for any kind of product, right? So do not just confine your understanding to the Greeks being to the call and put. Yes, the Greek applies to any product. And suppose you have a different model, right? You have a different model. Let's say that later on you will look at something like this. Okay, and we will extend it to a jump model. Well, this is called a Poisson process. We'll talk about very soon. Okay. So basically, the benefit of this model is it allows your stock price to jump, okay, to jump. Instead of moving continuously, it allows it to jump. So, but notice, right, when I write it down here, I have introduced an extra parameter, lambda. Lambda is the rate of the jump. So you see, if I were to price even like a vanilla call option on this product, on this model, then suddenly I have an extra parameter here, lambda. How often does the stock jump, the rate of the jump? Certainly the sensitivity, right, of the stock price with this jump is a matter of my interest too. I mean, it's not a Greek in the sense that it has a name, right? Because people don't discuss the Greek name outside of the confine of the Black-Scholes model. But right, as a quant, and if you build your model, right, it makes sense that your boss will ask, okay, what's the sensitivity with this new parameter you introduce, right? So again, I'm not trying to say that, right, there's any explicit formula for this out there, but you should be able to think your way through on how to approximate, if you could, on this quantity, the so-called Greek with respect to this lambda, okay? And by the way, this lambda may have a very practical interpretation. It may be, right, this is a jump process. So, I think stock price may react to, like the Fed fund rate. Like basically, like, if the Fed meets, right, they may decide to raise the rate or not, okay? And they have a frequency of meeting, right? So, and then in the meeting, they may not decide to raise the rate or change the rate. That could be a jump. So you could, right, model this right here from the Fed meeting rate, the Federal Reserve, right, meeting frequency. So anyway, right, that could be one interpretation. But of course, then you want to understand how your stock price is sensitive, or sorry, right, not S, V, right? That's not S, V, DV, right? The option based on the stock, right? How your option is sensitivity, right? Not to the interest rate, right here. That could be something, but you could be interested in how your option is sensitive to the Fed meeting frequency, for example, right? Any question? All right. So then the next concept I want to introduce, right, is the idea of delta and gamma neutral. And actually, folio. And actually, this can be extended, right, to something like Greek neutral. You can make any Greek neutral, actually. So neutral means close to zero, okay? Neutral means close to zero. Neutral means close to zero, all right? So suppose, like, right, I mean, let's say you have a portfolio, and let's say at the beginning, it only has a call option, one V call, okay? So the delta of the portfolio, right, at this current moment will be, right, the delta of the V call, which is ND plus, right, and which obviously is non-zero. So what this means, right, let's say from a trader's point of view, is that this portfolio has risk, right, or is sensitive to a movement of the market, because if the stock price moves, then this portfolio will move, all right? And again, right, I mean, you may think this is non-intuitive, but it's undesirable, right, sometimes to have your portfolio move, right? Because who knows what direction it will move, whatever. So the desirable thing to do is to make the delta of this portfolio close to zero, all right, or as close to zero as possible. What you want is to add product, okay, to the portfolio to make its delta close to zero. All right. And this, by the way, is a very real activity of the trader, okay, in practice. I mean, of course, not as simple as this, but like I said, right, they have their Greeks within certain threshold, okay, certain tolerance level that um, they must, follow. And so if somehow at the beginning of the day or something, they see that their Greeks is outside of that range, then they need to trade, right? They need to perform trade so that, right, they bring it down to the acceptable level that is prescribed to them, right? So here, for example, right, make it things very stylized and easy. Let's say the goal is to make the delta close to zero, or set, let's say less than 0.01 or something, right? Then something like this is not acceptable, right? So our trader has to go out and find some product. And right, so of course, what product is relevant here? The easy one, right? And this is, again, because it's theoretical problem, is very easy. What you want to do is you want to change, right, to the portfolio to one share we call, right? And let's say X share of the stock. So is big why? You ask why? Well, the reason is because the stock is, right, very correlated, right, to the call option. So if you want, the idea is you just somehow add stock to to your portfolio, and by the correlation of them, right, that's actually the thinking that goes on. You will be able to neutralize, right, the movement of the net movement of the stock of the portfolio when the stock moves, right? So the question is how much? What is this X? What is this X that you're adding, right? So of course, what's the goal? The goal is to say that the delta of the portfolio, right, is going to be close to zero. But what is the delta of the new portfolio now? It's going to be the delta of the V call, right? So let me just do delta call, right, plus X times delta of the stock. Is that okay? Now, and then you want this, right, to be approximately zero, or let's say it's zero here. We just set equal to zero. All right. Delta of the call is ND plus. What is delta of a stock? What is delta of a stock? Exactly, right? I hope it's very easy. Yep. So that's going to be zero. So that means X is minus ND plus. That it tells you, right, that very straightforwardly you short some amount of stock, and then you will bring your portfolio to delta neutral. Okay. Now, I'm demonstrating a very, so and you also see why, right? This is the delta of the stock too, right? This is the number of share, sorry, delta of the call option, right? ND plus, remember, is the delta of the call option, but it's also exactly, you see, the meaning is also the number of share you want to hold at any moment to make your portfolio of the call option delta neutral. So it has that meaning, right? Sorry, number of share you want to short, right? Not want to hold, you want to short at any moment, right? To make your portfolio of the call option delta neutral, right? So you see that, right, it's a very stylized, okay, problem. I can ask this question on a homework on the exam, right? Or very, like, for example, I have a butterfly portfolio, right? How do I make it delta neutral? You see, but the moment I move from a call to a butterfly, for example, you see the questions start to be a little more interesting, right? Because the butterfly is not as simple. But you see, then it can generalize to a portfolio of many, many products. Yes. And then how to find, right, something to buy that makes it delta neutral, you see, is a very interesting problem. Of course, the first interesting thing is to the calculation, but I would say that's trivial in the real world. The job of a trader actually is to find the right product to buy, okay? Because buying and selling, right, out there is not something that like we do here on the paper. Buying and selling costs money, right? The transaction cost. So how they perform and how sometimes you want to buy a product, it's just not there, right? I mean, suppose that this guy right here, whatever it is very hard to get a hold of. And God forbid, right? We don't talk about this kind of exotic situation, but there are option out there on something that is not tradable. For example, this goes to home with Sherry out there, but there's option on temperature, right? There are options on temperature. In other words, if the temperature falls below something, you get some money, okay? And the government obviously is interested in buying something like that, for example. Okay, if you have option on temperature, and I'm not kidding, right? There's such a thing, or option on rainfall. You're not going to buy temperature, right, to make your portfolio delta neutral. No one's going to sell temperature to you, whatever that means. So that doesn't mean that a trader does not, right, may not have a portfolio of call option on temperature, but how do they work, right, to make that portfolio delta neutral, right, is a very serious question they can ask. I do not know the answer to that, right? I know roughly they want to find some substitute product that will make it, again, the correlation, right, with the correlation is the key answer, but I don't know. But so, right, I mean, again, this is a very stylized answer, very easy to do on paper. In practice, right, there are many, many other difficulties that will show up. Any question? All right, so the second idea, right, and then is the gamma neutral, right, portfolio. All right, so same thing, but so first you may want to understand why someone wants the portfolio to be gamma neutral, right? Someone wants the portfolio to be gamma neutral because of this. That basically, right, that if you have a portfolio, let's say like this, right, delta neutral, something like this, okay, then basically what it says is, let's say here's a time, right, time 0 without lots of generality, because your portfolio is delta neutral, right, delta equal to 0. For a little time, right, epsilon out, your portfolio does not change in value. It's something like this, okay, it's delta neutral. But, right, you know that this is an approximation, right? As time moves on, right, the stock price no longer stays at the same level, right? So obviously the ND plus no longer stays at the same level. So in other words, even though your portfolio value stays, approximately constant, right, throughout this interval, when it comes to here, basically you are no longer delta neutral. Even if, right, you start out with delta neutral, you understand, right? Because the stock price moves. So even though you start out with delta neutral, it will work for a little bit. But after some time, right, very short time, you start to see that your delta start to slip away from 0. And then that slipping, right, will just gonna keep happening. Yes. So basically what happens then? Well, the answer is simple: rebalance, right? Rebalance your portfolio, right? So that's what, again, right, that's why a trader has to be there, meaning they keep the portfolio delta neutral today. Tomorrow, right, is still a little bit there, but it may be, right, a little bit outside the range. So they have to do a trade, right, to bring it back to delta neutral. So rebalance, right, rebalancing. But of course, right, besides rebalancing, what else can you consider? What else you can consider is to immunize it even more at the beginning. In other words, you can try to, add more product so that not only make it delta neutral, but make it gamma neutral. Why, right? What is gamma? Gamma, obviously, right, I understand, is the second derivative with respect to the stock price. But honestly, second derivative is an object that's a little bit abstract, right? People understand first derivative. Second derivative with respect to the original function is a little bit abstract. So in this context, right, I'm not sure if I'm talking too much, but you understand the meaning of gamma in this context that I'm describing. What is the relevance of gamma in this consideration, right? Like you understand, right, that when I go from here to here, my delta is no longer neutral, right? So why is it that immediately I think of gamma when I think of this problem, or when a trader thinks of this problem, she immediately thinks of gamma? You see, because the gamma is the sensitivity of delta with respect to the stock price, isn't it? Okay. Now I understand, right? Everyone knows that. The first derivative of the first derivative is the second derivative, right? But obviously, I hope I'm not saying something, too simple. That here is this interpretation of the gamma that is relevant, right? Of course, it's the same, but here is the sensitivity of delta that you're caring about, right? It's not necessarily the sensitivity of the original stock price, option price. You do, but right indirectly, right? Directly, this is what you want, because you want to maintain the delta neutral, right? Here, right, in delta neutral, right? In delta neutral, what you want to maintain is the portfolio value, right? You want to maintain the portfolio value. That's why you want it to be delta neutral. In gamma neutral, what you really want to maintain is the delta, right? You want to maintain the delta level. That's why you want to keep it gamma neutral, okay? So with that being said, right, you probably can have a gamma neutral portfolio without having it delta neutral. In other words, the delta is at certain level, right? You just keep the gamma neutral so that you stay the delta to be at the same level for a while. Anyway, right, that's the finance intuition behind it. But what is the math? The math is very simple. Again, right, let's just start with our portfolio above. Let's say that we have a portfolio of, right, now we have one call, right? And then minus ND plus, right, of stock, right? And our trader, right, is very happy with this portfolio because it's delta neutral, right? It's delta neutral. We show delta portfolio is equal to 0, right? What about its gamma? The gamma, right, of this portfolio will be gamma of the call option, right, minus ND plus times gamma of the stock. Is that okay? So I profess, right, I don't remember the formula for gamma. Does anyone remember the gamma? I don't. I don't remember the gamma. But anyway, right, I guess it's some number. But what is the gamma of a stock? Gamma of a stock should be 0. Exactly. So basically, the gamma of this portfolio is a gamma of the call option, which is, right, I don't remember the exact number, but it's not 0, right? So in other words, the gamma of the portfolio, right, this portfolio is not gamma neutral, even though it's delta neutral, right? It's delta neutral, but it's not gamma neutral. Yes. So in other words, right, you need to add product, right? Add product to make this gamma neutral. Okay. What kind of product do you think we can add here? So, right, basically the equation or the question then is, right, you now you have a portfolio, right? You have this, and say you have so many shares of stock, right? And let's say you have X in something else, right? What is that something else that you expect? Or what is that something else that you suggest? Well, here's an idea, right? I mean, there's no rhyme or reason to this, but obviously you cannot use a stock, right? You can use a stock to fix a gamma, because by definition, gamma of a stock is 0. So you cannot use gamma of a stock. You're going to use a stock to fix a gamma of a portfolio. You have to use something else. Well, you already have a call. What else can you use? Well, how about a put? All right. All right. So, right. So you understand, right? Because using a stock cannot fix the gamma of a call option. So you must use something else that has gamma non-zero. And the easiest product that we can just reach out to is a put, right? But so, right, what is the equation here that we are solving? Well, something like this, right? Gamma of the call, right? Because we have one share of the call, minus, right? So ND plus has nothing, so we don't do it. Plus X, right? Gamma of the put is equal to 0. So easily, right? X is something like gamma of the put over gamma of the call with a negative sign, right? So if I do this, then this portfolio right here will be gamma neutral. Right? Do you see any problem with doing something like this in the overall scheme that we're describing? Exactly. By fixing the gamma, you mess with the delta. Exactly, because that's exactly what I was expecting. Because this has delta non-zero, so you have to be careful, right? By fixing the gamma, you might mess around with the delta. Exactly, but when you do this, but not delta neutral. Exactly. Okay. So all right, you're like, what? Then what do I do? Well, you know. So the point is, right, that you cannot keep this at this level. So you have to actually resolve the whole equation. In other words, right, if your desire is to make it delta and gamma neutral, then your portfolio should be 1V call, because that's what you have, right? I don't know. The one is just like what your client asks you to maintain. Your freedom, right, is X in S and Y in the put. These are what you as a trader get to buy, get to decide, right? And then of course, then you solve for X and Y, okay? To make, right, delta of the portfolio, which is, right, delta call, right, plus X plus Y delta put is equal to 0, and gamma of the portfolio equals gamma call plus Y gamma put is equal to 0. Is that okay? And of course, this gives you an equation in X and Y that you can solve. Any question? Okay, so right, so I'm describing a procedure that is very routine and very popular, right? And the terminology gamma, delta, neutral. And then, but you see, right, again, that underlying this procedure, right, which is very simple math, is the calculation of the delta of the Greeks, right, of this op. So that's, I would say, right, from a quant point of view, this is easy, all right? How to find these products are the trader's job, okay? How to find these products are the trader's jobs. But once you identify the product, then solving this equation is easy. The harder thing is to calculate the delta, or you know, the Greeks of those guys that you want to buy, right, to determine the share price, to a tolerable precision, right? Because how precise you calculate this will affect how you calculate X and Y. And of course, right, the trader being your boss, whatever, right, doesn't have to find a product that makes your life easy, right? He may find something that because somehow is cheap to buy, right? He might find an exotic option or something out there he wants to add to his portfolio and say, hey, you know, go calculate this for me and make sure, you know, that is delta neutral. How many should I buy, right? And if it's something that non-standard, then you have to do the work to find what these Greeks are, so that you can tell them, okay, you need to buy so much. Okay, so many. Any question? All right. I think it's probably a good place to take a rest or a break for, let's say, 5 minutes. So let us reconvene, all right, at 10:05, and then we'll continue with our lecture. Okay. So let us continue. All right. Do you have any questions so far? All right. So on this topic, right? That notice that what the message is that, oh, I need to share, right? So even though I presented to you, right, delta and gamma neutral, which is the very traditional routine, right, topic, you'd see there's nothing that prevents you from looking at, for example, right, Vega neutral portfolio, rho neutral, right, etc. Right. It just depends on what you're interested in, right? You can just target that parameter and make it neutral, right? And so I'll just remark it like that. I just keep it as a remark like that, right? What do I want to say here? That basically it's a Greek neutral, right? Whatever Greek you choose, you can make it neutral, of course, right? By buying the appropriate product with the appropriate amount. Okay, so the next topic I want to talk about is the Black-Scholes PDE. All right, and the relation between the Greeks. Okay, so the Black-Scholes PDE traditionally, okay, is given for a call option. All right, and the point of view is this, that basically, you know, you have a a call option, right, on the stock price. Right, with expiration T, whatever, you know. And strike K. Okay. So the point of view is they say, well, your option price, right, V call, will be a function of two variables, T and X. Okay, like that. I mean, I'll explain. It's just the traditional way they say it. It sometimes is big V too. So T right here is the current time. Right, and X is the current stock price. Right. So the idea is that if you know what the current time is and you know what the current stock price is. So basically, right, this implies that the time to maturity is T minus T, right? So if you know the current time and you know the current stock price, you can plug in, right, for this function and get the current call option price. So the message here though, right, and I will explain it more mathematically. The point, right, even in this message is this, and it's a little bit interesting, is that the call option price, or actually a lot of option price, is a deterministic function of T and X. I mean, it's a function of like sigma and every other things, but it's a function of T and S0, if you will, T and S, if you will. Okay. It's important because, right, you understand that on this side, we're dealing with random stuff, right? The stock price is random, the call option price is random, etc. On this side, you're dealing with purely nothing random, okay? Nothing random, that's the emphasis. This V is totally deterministic. The question is how? Well, the how is that all the randomness has been built into the X. In other words, right, it says that as the S is still random for sure, but at any moment in time, it takes on a particular value, right? As long as you know that particular value and you plug it in, you capture, right, the whole randomness of the V. So the randomness of V is through the randomness of the S and nothing else. The whole entire structure is deterministic otherwise. And so, yes, so what I want to say is, my mind went blank. Yeah, this actually is a fancy way to say this is the Markov property. Okay, this is the Markov property of the stock price. This is the Markov property of the stock price that makes this happen. And in turn, this is due to the Markov property or the independent increment of the Brine motion. Okay, so these are the things that make it tick. These are the things that make it work. Okay, we'll explain. But anyway, right? Then the interest is this: if it's a deterministic function, what is it? Can you write down the formula, or what is it, right? Well, actually, you know what it is, right? It's S0 ND plus. So obviously, right? Actually, okay. So to make it even less mysterious, it is this, right? X ND plus minus K e to minus RT ND minus, right? Where D plus minus is R plus minus 1/2 sigma square times T minus T, right? Minus log K over X divided by sigma square root of T minus T, right? I hope that's clear. So basically that's what we mean. Anyway, right? What may be a little bit more surprising is this function also satisfies a PD, right? A partial differential equation. That mysterious topic that you are asked to have the prerequisite for this program, right? Why do you have to know PDE? Well, PD shows up in this kind of things. So what PD are we looking at? The PD is V sub T plus V sub X R times X plus V 1/2 V sub XX sigma square X square is equals to R times V. This is true for any X, I guess any X positive, and any T between 0 and big T. And the terminal condition is X minus K plus. All right. So this is the PD, right? And why, I guess why is it called PD? I guess it's clear. It connects a partial derivative of T with a partial derivative in X, right? And those of you who has taken 421, 423, whatever, this is like a variation of the heat equation. If you don't take this term, if you take this term out, then that's exactly the heat equation. Okay, it's like a heat equation. So, I mean something here too, but right, this actually is referred to as the Black-Scholes PDE. All right. All right. So what does it do? Several things. Here, potentially, it gives us an alternative way to find the value of V. Okay. Basically, I guess you may be going through it now or not, but in numerical analysis too, right? One of the topics should be how to solve PDE numerically. And so basically, the point is, right, if people get a hold on a partial differential equation, they can solve it. And after they solve it, of course, they'll get something like this. Okay. So you're like, okay, what's the point? Isn't this easier? Why do I have to work so hard, right? Numerical PD is so tough. The answer is sure. In this point, I myself wouldn't be bothered with this, right? Go with this. But in more complicated setup, all right, in more complicated setup, like exotic option and other things, right? By the way, if the world's full, it's just filled with like call and put option, vanilla call, vanilla put, we won't have a job because, right? Why bother? Everything has been worked out, right? You have a job because there are more complex products that needs to be studied. So for more complex stuff, then it's hard to tell which approach is easier, right? In more complex product, you won't have this formula, as I told you, right? Because the expectation cannot be taken so easily. So in that context, maybe the PDE, being as scary as it is an easier way out when you are calm when you look at it. Okay. So the point being now is that this gives you two alternatives to get to the same formula for the call option price, okay, or for the derivative price. That's all I want to say. Okay, it gives you two alternatives to the derivative price. One is stochastic, one is deterministic. Okay, and if you are interested in math, this is super interesting because these are two different fields of mathematics with their own different toolbox. So anytime you have two approaches that use two different approaches, two different toolboxes, that's exciting because that means you can always jump between, or you see the connection between one field and another. All right, but that's probably a little bit beyond us. But so the point being is, I just want to say this is the Black-Scholes PDE. It has financial meaning too. That's what I'm more interested in showing you. And I want to show you the implication, right, of what this means and how we will do, right. We'll for the future chapter, when we look at products, we will always mention the PDE and the stochastic formula, if we have any, the stochastic calculation. These two ways to do it. Any questions so far? All right. So now, I'm not sure if this is scary or not, but stare at this for a little bit, right? Do you see what these objects are in terms of finance? Gosh, I can't see the chat. I should try to. Give me a moment, all right? Yeah, they are the Greeks, exactly, right? This is the gamma, the delta, and the theta. So from the financial level, right, the Black-Scholes PDE connects or provides a relation among certain Greeks. Okay, and you can be sure that the Black-Scholes PDE usually connects the theta, the gamma, and the delta. That's usually what it does. It may involve some other terms, but that's the most traditional one, and we'll say why. But basically, from the point of view of the Greeks, right, it says theta plus delta, right, times R times the stock price, plus 1/2 times gamma times sigma square stock price square is R times the value of the option. At any time, this is true. At any time, this is true. And I like to do this. I think people also sometimes do this. Yeah, is routine, is traditional to write the PD equal to 0. So minus RV or minus RV is put in front. But this is this. Okay. So this relation, right, by the way, is super interesting because it tells you that, right, these guys are not independent. These guys are not independent, right? At any time, if you know 3 of them, you know the last one. So if you have the gamma, the delta, and the theta, then V must be determined. All right. So in that sense, I'm like right, you think an option has many other things, right? It has the vega, it has the rho, etc. Here it says that, yeah, it has the other, Greeks as well, but these three Greeks, in a way, right, uniquely determine the option. All right. So if you know these three Greeks, then the option price must be determined, right? At least for this type of option. Okay. For European option, as we'll show you. So if you know these three Greeks, then you know exactly it must be a call, a put, or butterfly, that kind of thing. It cannot be anything different. Okay, that's super interesting. Or conversely, suppose you know the option price, the theta, and the delta, then the gamma is uniquely determined. Right? You cannot run around. It cannot be arbitrary. Okay. So we'll explain why later. But this also has implication in trading. All right, it has implication in trading. Anytime you have some connection between the Greeks, you can be sure that there's some implication in trading. All right, we'll talk about this later soon. But first, right, let me just show you. I mean, I think you trust this, right? There's nothing fancy about it, but it's always cool to see, you know, things in action. So let me show you, right, the program which I posted, right, online already. Right here, right? This is a Black-Scholes PD, which I think you might have used to run the the homework this week already, right? But I want to draw your attention to this little thing right here, right? You see here, I just calculated delta, gamma, and theta, right? And I form something like this here, like the Black-Scholes PD, right? Or basically, it's just combining the Greeks. If the Black-Scholes PD holds true, this thing should be 0. Okay, so here, right, this is for this kind of thing. I mean, I don't know. We can mess around a little bit to change the parameters and show you that nothing will change, right? Like this. Right, so 1 to the minus 15, that's close to 0, right? So of course, anything, any parameters, right, as long as you combine like this. So the point is, at any moment in time, right, at any moment in time, whatever these parameters is, you combine this, you get 0, right, for the Greeks. That's the point. Okay, so what so the next thing we're going to do is to show why right. So the next thing we'll show is to show why, right? So why, right? Why the Black-Scholes PD hold, and then also you know, the implication of this in trading. But first of all, right, let me ask you this. I say, right, this is a call option, right, and this is a Black-Scholes PD. Does it hold for the put option? I think I did say that, but how do you know that this same equation holds for the put option? How do you know that this same equation holds for the put option? Without, right? Let's say without, you say, okay, I just know that it holds. Because I think if you look up on Wikipedia or whatever, right, they will state this for the call option only, as far as I can tell, right? Why does it hold for the put option? Or does it hold for the put option? So maybe like this, like, does Black-Scholes PD hold for put option? If so, what does it look like? Does it hold for butterfly, condor, that kind of thing? Okay. In other words, right, do the Greeks of those derivatives behave in a similar way as the call option, and why? How would you explain that? Yeah, maybe for an interview question, right? Someone asked, you know, so we know that Black-Scholes PD holds for the call. Can you explain why it holds for the put as well? Anyone? All right. So the idea, right? The idea where you can try to say that it holds for anything like this. The idea is bilinearity, that's all. Okay, and linearity, I think, is something you should have learned from numerical in PD, that kind of thing. So what is it, right? For example, let's just look at the put, right? So first of all, right, if you want to be more precise, this is what you're claiming right now. Yes. And the interviewer is asking you for the put version. Yes. So he or she asks you to explain how to go from here to here. So put it in this way, what is the, I don't know, what is the intuition or what's the guess? Even a bad guess, right? What is a guess? How do we do this? Anyone? Well, right, the answer is to connect the two. Yeah, but how would you do that, Don? Can you be more specific? Oh, no, 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 no. Yeah, connect the two, but I think the first one you say is you say R sigma. R sigma are not Greeks, right? R sigma are the parameters of the equation. Delta is Greek, right? Greeks are here. These are parameters of the equation that never change, or are supposed to be constant here, right? Yeah. So the first one you say is not related. Yeah. The second one, yes, but how would you connect the two? Well, by obviously connect the delta, the Greeks of the call with the Greeks of the put, frankly speaking, right? We're trying to explain how we go from here to here, Sherry. So, right, I mean, someone asked, yeah, I learned from the textbook that this is true, right? I accept it. It's mysterious, but I accept it. But you claim that the same thing holds for the put too. Can you convince me why? Yes, from the first, right? From a starting point. Does that make sense? Or right later on, you see the ambition is to show it for anything that's vanilla, anything that's European. You're almost there, Don, but you're not precise. Are you sure the Greeks of the call and put are the same? Is delta of the call is equal to delta of the put? No, no, no. What Don say is almost there, Kashif. Correct. Only gamma of call equals to gamma of put. Yeah, no Kashif. These are fixed quantities, okay? These are fixed quantities. They're not, you don't want to sum them. All right, Sherry, why are the gamma equal and the delta not equal? Or anyone actually, not just Sherry, right? Why are the gamma equal? Yeah, anything else equal from the call and put? And what's different? And how do you know? Right? Another easy interview question, right? Between the Greeks of call and put, which one are the same, which one are not, and why? Well, again, right, when someone asks that kind of question, or when that question shows up, you know that the link must be somehow there's the link from the put and call. What is the link between put and call? What is the link between put and call?
Put-call-parity?
Yes, my man, you're well trained. Put call parity, exactly. Right, that we have put minus call is equal to forward. Yes, or v put minus v call is s minus k e to minus r. Let me do tau here, right? Tau for the time to maturity, right? So from this equation, can you tell me how delta put and delta call are related? Oh, sorry, call minus put, right? Not put minus call. Sorry. Put call parity, but it's call minus put. Call minus put. Delta call minus delta put is 1. Gamma call minus gamma put is 0. Right? Theta call minus theta put is r k e to minus r tau. There could be a minus here because they define theta as minus 0 to respect to tau. Right? And that's it. You see that after you plug in here, then you can replace v put with this delta with this gamma is this, and you can check that it's exactly 0. I'll leave it for you as homework. But you see that that's how you would go from here to here. Question. Is it okay? How would you prove that, or how do you expect that something like this equation holds for the butterfly spread or the condor spread? Yeah, right. I mean, not that they're same, right, Don? But like, so for example, from here, right, you can plug in the theta of the put, right, like this, and you plug in the delta of the put like this, right? And basically, then you know, or you can just start here, for example, and then plug in the call version, right? And things should cancel out. Yes. So yeah, right. Do the equation hold for butterfly and whatever else the spread that we look at? Do they hold, and why? The answer is they do, right? Holds for the spread because, right, I mean, delta the spread, right? Let's say delta butterfly is delta of, call K1 minus 2 delta call K2 plus delta call K3, right? And same for gamma. Yes. And if these guys line up like this and set up to be 0, then this side also should be equal to 0. Is that okay? And that's linearity. That's all there is. Okay, question? But right, at least you should be able to see that, you know, from the call equation, you can deduce all these things. But what's more, even more, right, more than this? Last thing I said about this, Cherry, I say, right, because you have the combination like this, right? Basically, simply speaking, right, butterfly is synthesized from a call, right, from a portfolio of call. If the portfolio of the call follows this kind of Greek relations, then butterfly should also follow, right? But I mean, mathematically, basically you add this side and you add this side. But right, this side goes to 0, so this side goes to 0. It's just too tedious to write down, but I hope you see the idea. You understand what I'm saying? Yeah. But I claim, right? I claim that this is not obvious, but it's easy. In other words, if you think about a little bit, right, you can, I'm sure you can work out these details. Okay. Now, what is more surprising, right, is this. This actually holds for any European product. Okay. In other words, suppose that you have, and this, by the way, is very popular, but you may not see this, the log of a stock price. Okay, a log of a stock price. This shows up in variance swap. Okay, I don't think we have time to talk about this in this class, but you know, just basically it falls under the formula like this, right? Just some function of the terminal stock price. Okay, it so happens that you choose a log, then you're dealing with something like a variance swap, but it's a function of the terminal stock price. Okay, so here, right, basically I think the log makes it easy to price, but basically if it's phi in general, right, then VT, right, the value of the stock price, sorry, the value of the option at time little t will still be a function, right, of T and ST. Okay, where, you know, this is from a structure of T and X, but this is no longer explicit. No relation necessarily to the Black-Scholes formula. All right. What's the reason? The reason is this is no longer, you know, a linear function or the, you know, this kind of max function from the call, right? I just pick something like the log function. All right. It is not necessarily related to the call in any way. But the mathematical structure still tells me that it's a function of T and ST. I just don't know what the function is. But then the abstract claim is that the Greeks of this option, right, this new one, will still be, it still satisfy Vt plus V sub x Rx plus 1/2 V sub xx sigma square x square is equal to Rv. For this one, for this new product, for whatever this one is, okay, as long as it's European. All right, and under Black-Scholes model, you understand, right, the importance of this. The above, you can explain it clearly because you can calculate it. All right, butterfly, put, call, you have formulas. Here, this is abstract. All right, it's abstract because this is whatever function it is. But the claim is whatever function it is, the Greeks still follow this formulation. All right, that's the importance. And again, right, you ask, well, why do we care? I only deal with call and put in this world. Not really, okay? Because of this. For example, the variance swap is a very important product. And like I said, right, trust me on this, or you can look up on the internet, log price as a derivative somehow, as an abstract derivative, somehow is related to a variance swap. Okay, So what we want to establish is that this is true, right? Because you see, if we can establish this, then mathematically, of course, it implies that it's true for put, call, butterfly, whatever, because they are all, right, some kind of function of ST. Okay, that's the goal. Any question? All right, so I want to, right, so it's going to be a little bit abstract, right, from here on a little bit. So let me bear with me, all right? So first, I want to establish a structure of VTX as an expectation. Okay. So VTX, right, basically is conditional expectation of discounting back to time little t of the payoff condition on, right, this. Yes, this is a pricing formula. Except that, right, actually, when we do this, we say more than just conditioning on this. We say that we are conditioning on the current stock price being X. Okay, that's the case, isn't it? All right. How do we even calculate this, right? This is so crazy. Well, it's not in some way. Well, you start out by unraveling. It's really have that same flavor as decomposing the future in terms of the present when you do conditional expectation in the exercise, from the homework before. You write down what future ST is in terms of current ST. It's going to be X, right? And then you do e to the r minus 1/2 sigma square t minus t plus sigma w tilde t minus w tilde little t condition on st equal to X. Is that okay? You see what I'm doing? I mean, I overflow here, but this whole thing, right, is just st in terms of s little t, which is X. Okay. So here's the deal, right? Here's the deal. Here's the deal. The deal is you may think, right, that immediately that this is a future movement of the prime motion is independent of the information here, right? Everything else is a constant. So it seems like there's nothing conditioning here, right? The conditioning only happens because you replace, right? Technically speaking, it should be ST, right? Like this. Let me do this. Yeah, maybe this is more rigorous, right? There's ST here, right? S little t here, but you only know ST equals to X. So what happens is a very intuitive move, but it may be a little bit crazy mathematically if you think about it. Like that. Okay. So what you see what's going on here? What's going on here is I replace this guy here, which is supposed to be a random variable, right? Because the stock price at time little t is a random variable, with a single X. And then drop the conditioning. So this is purely just an expectation. This is no longer conditional. This is just purely an expectation. All right. But it's an expectation with respect to what? With respect to this random variable right here. This is expectation with respect to this random variable right here. Okay. Now it's still not easy because this function phi right here could be something complicated. All right. But the accomplishment here is that you remove the conditioning. You remove the conditioning into an expectation. And anytime you can accomplish that, that's easy. Why? because, right, this is an advanced topic in simulation, but simulating conditional expectation, as far as I can tell, is still a very mysterious object. It's hard. But simulating expectation is easy. You guys have been doing this. I have been doing this in this class. Okay, simulating expectation is easy. Simulating conditional expectation is I think still a current topic of research. Okay, so anytime you can mathematically reduce conditional expectation, right? You know why we have to do it, because this is pricing at time little t. We have to do that. You can reduce it down to expectation. Then, right, even though the formula is hard calculation-wise, you can just chuck it into a program and ask it to calculate for you. Because, right, all you have to do is generate, right, sample of this, and then evaluate the value and average it out. And then you get approximately the expectation. Is that okay? So that's what I mean by the structure of this as an expectation. When you get it down to here, you say, I'm done. You can write it down as an integral, but it doesn't illuminate anything, right? Like you could write down as, I'll write one more, right? This is purely decoration. All right. So what am I saying here? What I'm saying here is, right, you're curious on what this expectation is. It's an integral of whatever this guy is against the density of this, right? Right here. And what is the density of this? Oh, sorry, right? The density of this is a normal with variance t minus t. So, so this is normal, right? With mean 0 and variance t minus t. That's all, right? So again, right, very abstract mathematics, not too abstract, but it has value. Its value is it allows you to evaluate, right, the option price as a pure expectation. And the reason why it works, right, is because of the independent increment of the prime motion. All right. And this is so important, it has a name. I know we don't use the textbook so much in this class, right? But if you look up, I forgot already, Shreve chapter 5 or something, it's called independence lemma. Okay, the independence lemma. I suspect Professor Larson might have mentioned it at some point too. I'm not so sure if he does. Did he? But anyway, right, this is an important mathematical result. Awesome, Sherry, thank you. Right, so I'm quoting independence lemma. All right, and I guess I'm repeating something that you should be an expert of. But yeah, so right, so the independence lemma applies here as well. Okay, to allow you to evaluate a European option as an expectation. And I'll stop here. All right. Okay, so that's a first step I want to establish. The second is a proof of Black-Scholes PDE for any European derivative. Okay, any. That's the keyword. That's the value. Right. In other words, anything like this follows this. And how is this true? How is it true? Actually, you may be surprised to hear, is actually from Ito's formula. Okay, and that's why Ito's formula is important in this business. I'm pretty practical, okay? I mean, I know you have to learn some theory, but I want to show you that you learn some theory because it has some connection to practice, right? You notice that, right, even though, right, the Black-Scholes PDE, right, sorry, where am I at? Right here. The Black-Scholes PDE, right? It connects the Greeks, but it doesn't pick the Greeks arbitrarily. It picks some very specific Greeks. It picks the delta, sorry, the gamma, the delta, and the theta. But these are exactly the terms that show up in the Ito's formula, isn't it? That's why, all right, the Black-Scholes PDE works that way, because it picks up exactly the terms that show up in the Ito's formula. Okay. Otherwise, right, why not the Vega shows up in the Black-Scholes PDE? Answer, Ito's formula does not contain anything differentiating with respect to sigma. Okay. So from Ito's formula, right? But specifically how Ito's formula comes in here. It comes in here like this, all right? And before we do that, let me say something. So we look at Ito process, right, at some point. Ito process is this, that dxt is alpha t dt plus sigma t dwt, right? Let's call it beta, right? So basically, Ito process anything with a dt term and dwt term. One more thing that I mentioned before is that if you have a stochastic integral or Ito integral, is a martingale. Okay, it's a martingale. So you know, again, right, in a class that I want to emphasize more mathematics, then I would spend, you know, I don't know, quite a few time in the class to show you why this is true, etc. All right, here I want to emphasize more practice. So I would ask you to accept this, right? If you want more explanation, feel free to ask me, you know, in office hours or, you know, after class, I'll be happy to explain. But if you accept this as a martingale, then the consequence that's important for us is this, right? An Ito process is a martingale if and only if it has no drift. That is alpha t must be 0. Okay. So in other words, if you have a drift term right here, you have a dt term, then it will spoil the stochastic integral. It will give the stochastic integral a direction. So it cannot be a martingale. It cannot, on average, stay the same. Okay, that's very intuitive, right? For example, I mean, the easiest one for you to think of is like this, right? Let's say xt is t plus wt, right? The Brownian motion is a martingale. I hope that's clear. But when you add t to it, what are you doing, right? If you add t to it, and you can try to, right, by the way, you can try to plot this on Python, right? It will start at 0 and it will move, right? But you will see that the Brownian motion path tends to increase with time. Why? It gets pushed by this. Okay, so if it tends to increase with time, clearly it's not a martingale because a martingale should stay horizontal. Okay, so if you generalize that, then anytime you have some kind of drift, then over a small interval, you see that you will have a tendency to go up or down, and that will prevent you from being a martingale, right? And Professor Larson may mention the term sub or super martingale, right? This is a sub martingale, for example, but in general, it doesn't have to be either one. It can be a semi martingale, but you know, never mind that, right? The message I want to say is an Ito process to be a martingale must have no drift term. Is that okay? Can you accept that? Any question on this? All right. So how does that come into play with our, you know, Black-Scholes PD? So basically, right, we showed, right, from the expectation structure, from the independence lemma that if you have a European option, then the option price process, okay, is a function of T and ST, where V is a deterministic function. Is that okay? So this is the guy, right, that would give us theta and delta and gamma, because this is the guy that we will differentiate with respect to x with, x twice with t, right? So this is the guy. So we transfer the abstract structure of the option price process into a deterministic structure where we can say, yeah, the derivative with respect to t is theta, derivative with respect to x is delta, twice is gamma. Okay. All right. Well, but what does this guy do, right? What does this relation tell us? What does this relation give us? Well, one thing, right, that because of risk neutral pricing, e to the minus r t vt is a martingale. Okay. The discounted option price is a martingale. The discounted option price is a martingale, right? This is a generalization of e to the minus rt st is a p tilde martingale. And I hope this is something that Professor Larson has mentioned before in his class. It just comes from the generic pricing structure. So I won't prove this. I won't show this unless you want to see. This is okay. That the discounted option price is a martingale under risk neutral probability. This is okay, right? So let me know if it's not okay, all right? If you need explanation. So accepting this, all right, accepting this, then, right, we will use that remark that something is a this guy right here will be an Ito process. Why? Because it's a function of ST, and ST itself is the Ito process. So we'll use this and try to find what its dynamics is. So the idea now is, right, VTST is an Ito process because ST is an Ito process. If it's an Ito process, we can use Ito formula to find dVTST. Sorry, not this, right? I would say the whole thing, Ito minus RT. Yep. Okay. But it's also a martingale. It's also a martingale. But if it's a martingale, then whatever I find here, right, is something dt and something dwt. I don't care what the dwt is, but the dt part must be 0 by my remark. And from there, I will get my Black-Scholes PD. Any question on the logic here? Okay, so let's do it, right? So d e to the minus rt vtst, right, is, well, first you need to differentiate with respect to t, right? It happens in two places. So it's going to be minus R, right? And then plus VT, right? V sub T. And then times this, right? So that's a product rule. And then you differentiate with respect to X, right? And then you multiply with dst. And then you differentiate with X twice. And you multiply with the quadratic variation of st. So here I'll just write V, right, to make it easy. No need to show the dependence. Is that okay? That's Ito's formula. Okay. So what is dst and the quadratic, right? Remember, the Black-Scholes model says this is rst dt sigma st dwt, right? W tilde. So the quadratic variation, right, is sigma square st square dt. Okay. And remember, we don't have to care so much for dwt term. We only need to group the dt terms together and set equal to 0. So what's the dt term? The dt term is, right, minus r plus vt, right? Oh, sorry. This is crap. Minus r times v like this inside, sorry, right? Because if I differentiate with respect to this, I got minus r times this times v. Differentiate with respect to t, I got vt times this. Okay, so the v is inside, I'm sorry. Okay. So that I get minus r times v plus v sub t, right? And then I got v sub x, right? But I only care for the dt term. So I got v sub x times r times st. And then I get v sub xx 1/2 sigma square st square. Everything times e to minus rt, right? That's just a nuisance. But you need it to pick up the r. So, right, this is everywhere. So I factor it outside. This is the dt term. And if you care to know, right, the dwt term is, or w tilde rather, right, is e to minus rt vx sigma st dw tilde t. Okay. But we don't care about this. We don't care about this. We care about this because we know this is the martingale. Any question? But knowing that this is a martingale means that this must be equal to 0. So the whole thing here must collapse, right? Whatever this glorious structure is, because my discounted option price is a martingale. You see, that's how the things are connected. Because the price, right, doesn't move in terms of average. Discounted price doesn't move in terms of average. All the Greeks that makes up the drift term must cancel each other out. So that's the Black-Scholes PD. Any question? Okay. So I hope, right? I mean, this is a bit of abstract math, but I hope you see the point is it established that the Black-Scholes PD does not just hold for call, put, butterfly, that kind of thing, right? Those are easy. You can establish with formulas. It holds for anything, right? Any European option, sorry, not anything, but any European option under a Black-Scholes formula. The reason is because of the Ito's formula, the Ito structure, and the martingale structure. It forces it, no matter what, right? The terminal value is, no matter what the payoff function is, this must hold. Okay. All good. All right. So now let's connect this with implication, right? So this connection with hedging portfolio. So we did not talk about hedging portfolio so much in this class, right? Because, you know, its continuous time context is not that easy to establish it, but this is the time to do it. So here's a question, it's very easy. Question, right? Suppose you hold an option. This is European, right? And for the sake of simplicity, right, you can think of it as ST minus K plus, that kind of thing, or butterfly, right, etc. And of course, you know V0, right? V0 is given. This is just the price, right? You're selling this option to someone, right? So this is how much you receive from selling the option, right? So in other words, I mean, I guess in trading language, you're taking a short position, right? In this option, you're selling it to someone, right? And you have to pay it back at time fee, right? You're shorting this. You're taking a short position in this transaction. But taking a short position doesn't mean that you just collect the money and sit there, right? You must invest in the market, right? You must invest into a portfolio, right? To cover your position, to hedge your position, right? So in other words, you need to invest, right? Invest in money market, right? And stock, right? To cover, right, the position, or to cover your exposure. Meaning that, right, you want, let's say, right, at any time t, let's say you hold delta t share, right, of S. How would you decide delta t? Or let me call it X, all right, to make it more distinguished, because we'll see delta show up later. Decide xt so that we can replicate hedge our position. Is it okay? I mean, I did not write everything down in you know, mathematical details, but I hope the finance makes sense. In other words, right, you sell this option, so you receive some money at time 0, right? But you owe some money. I mean, if you look at the call option, for example, right, it's always a positive payoff. So you owe some money back, right? Some money is due at time big T for you. So receiving this big chunk of money, right, you want to then start buying stock or something, start trading, right? So that, right, when this money grows and change, right, subject to the randomness of the market, meaning the randomness of the stock price, no matter what it is, at the end, you cover your position, meaning you have from your portfolio this amount to pay back, right, the investor. Does that make sense? The question is how? What is the you know, what is the share that you will buy? All right. So I think this kind of question has been addressed, right, or shown to you in Math Finance 1 by Professor Larson. I think Sherry mentioned something like that for the discrete case, right? You did something like that. The difference right now is a continuous time context where there's no discrete time points, right, that's available for you to compute anything. That is why I did not mention it right until now. because we don't have the tool to deal with it yet. Okay. But so first of all, let me say something like this, right? You obviously want to invest in two things: the money market and the stock. Here, I just asked for the shares of the stock. What about the money market position? What about the money market position? What about the money market position? How much do you invest in the money market position? Well, the answer is this, right? If at any point, right, the hedging is perfect, then the money market position, right, then the value of the portfolio, of the hedging portfolio, is always V little t, right? It's always the value of the option at that current moment. You start out, you have your portfolio being valued as V0. Then you go ahead and invest in money in stock, right? And then if you do it right, then at any time point, right, this value should be the value of the call option at that time, of the derivative at that time, okay? So in other words, right, how much, so of course, this will be, right, I would do this. It will be YT, right, plus XT times ST, where YT is your position in the money market. Okay, the YT is your position in the money market, right? So in other words, right, that XT right here, right, XT right here, oh, sorry, YT right here, right? If you want to decide it, the answer is simple. It's just whatever that is left, whatever that is left after you have accounted for the stock. So in other words, YT is VT minus XT times ST. That's it. And why do I say this? Because, right, XT is what you need to figure out for the question, but VT is known, right? The value of the call option at any time point is known, like from, you know, Black-Scholes formula or just from the abstract calculation of the expectation. So this is known. You need to figure this out. The stock price is known, but if you figure this out, then the value of your position in the money market is also known. Is that okay? So that's not something you need to figure out. It's given from the problem, in case you wonder. All right. So the only mysterious thing is what's the share of the stock that you need to hold at any time moment. The rest automatically follows. Okay. Any question on this? All right. So next, right, let's talk about the dynamics of a self-financing portfolio. Okay. So the point, right, of the portfolio being hedging, right, or replication, is that whatever money you receive from time zero, you have to use that to invest and trade. You cannot ask like your friend to say, I'm not doing very well. Can you give me some more money to put into my portfolio to help me hedge this position? That's cheating, because that's not what we think of, right? By trading well, right? You can also not say that, oh, I'm doing very well. Let me take some money away from the portfolio, right? And do some buy myself, you know, a new iPhone or something, right? So the whole point of self-financing, or the whole point of replicating, is whatever money you receive from the transaction, you must completely put that into the market, right? I mean, if you don't use it to buy stock, then you must use it to save money in the money market account. You cannot take it away. So in other words, that, okay, if you have your portfolio, right, let's call this V portfolio. all right, at any time point to be a position in the money market and the position in the stock, then the change in your portfolio, okay, value can only result from the change of these two positions and nothing else. How would that happen? It would happen by this guy earning an interest over a time interval, and this guy moving. Is that okay? This guy moving. Is that okay? So this right here is exactly what self-financing means. In other words, right, the change in the value of your portfolio completely comes from the interest rate you earn and the movement in the stock price and nothing else. Okay. Now, so plug in, right? Plug in this. You see, this will be, right, YT is V of the option at time T minus XT times ST, right, R dt, and then plus XT dst. Okay. But what is dst? dst is R st dt plus sigma st dw tilde t, right? So in other words, you see that this term cancel, right? Giving you with V option, right? T R dt. What do I have left? Plus xt sigma st dw tilde t. Okay. Sorry, I'm blanking out a little bit. Give me a moment. What I want to show you, somehow I'm not seeing the connection here, but what I want to show you is that if you hold this to be the value of the delta of the call at any time, then the V portfolio at time t will be equal to V option at time t. That's all I want to show you. Okay. Somehow I don't see how this will lead me to that. So I think I'm missing something here. I'm missing something here that I don't want to kind of make you wait over it. So the message that I want to make is quite simple, that to replicate, all right, to replicate any option like this, to replicate any option, what you want to do is just to hold at any time moment the delta of that call option. Okay. Sorry, the delta number of shares of that option. So it's almost like you keep the portfolio delta neutral at any time point. But if you do that, in theory, if you do it perfectly, then you will be able to hedge the portfolio. You will be able to hedge that option completely. All right. So here I fail. I missed something here. I don't see the connection. So I apologize. All right. Let me go back and let me look at my notes and see what I did wrong. Did I do it wrong, Sherry? Because here xt st r dt, right? I also have xt rst dt. So don't they cancel out? Am I wrong? If that's something wrong, then that may be that may be something. But no, it's fine, right? But what I'm failing to see here is somehow I want to show that if this is the delta of this option, okay, then you know what? I think I know. I think I know. I think I know. It's this, okay? I think I know. Actually, I think I know. Let me continue. Actually, I think I know. Thank you for asking the question, Sherry. Somehow it clears my mind. If I replace this, right, then what I have is something like this. That this is V option, right? RDT plus delta, right, of option, right? At time t times sigma st dw tilde t. Okay, like that. Yeah. Okay. Let's continue. I think I pick up my thread of thought now. Okay. So what I have shown, right? What I have shown is that the change in the portfolio is related to the change of the option like this. Okay. In the sense that it's related to the change in the option by the option price and the delta of the option. Okay. If I choose number of share I hold is the delta of the option. Okay. Now what I want to accomplish, right, to show this, all I need to show is this is equal to the change in the option. Then I'm finished. Then I'm complete. Okay. Do you see that? If I could show that somehow this is the change in the option, then I'm done. Why? Because then I say that the portfolio change is equal to the option change. All right. But the option and the portfolio start out at the same value. Where is it? Right here. The option and portfolio start out at the same value because whatever you receive for selling the option, you use that to invest in the portfolio. So if, right, the portfolio and the option always has the same change, the same differentials, then of course they end up at the same target. Is that okay? So if I can show this is equal to this, then I'm done. All right. Are we okay with this? But this actually was already in the proof of the Black-Scholes, right? This is in the proof of the Black-Scholes. Okay, so first of all, let me pause, right? Any question here in terms of the logic that I want to show? Okay. So now, why is this true, right? Why is this connection true? Well, the option, you see, the option, right? If the option is a function, right, of t and st. So the change in the option, right, a change in the option will be the theta, right? Let me just call theta. dt plus delta, right? Option s dst plus gamma 1/2 gamma of the option sigma square, right? Gamma of the option dst, right? Like this. This is Ito's. Right. But, right, what is the dst and d quadratic? That will be, right, let me just write theta now, okay? Theta plus delta, and this is rst dt plus sigma st dw tilde t plus 1/2 gamma sigma square s square dt. Now, by Black-Scholes PDE, you see theta plus delta R times S plus 1/2 gamma plus this plus 1/2 gamma square sigma square S square is R times V, right? By Black-Scholes PDE, this is R times V. And the only term left is this. Is that okay? So that's my point, that the dynamics, right, of your portfolio from self-financing, when you trace it down, it comes to this term. Then by Black-Scholes PDE, you discover that is exactly the change in the option price. Okay. So it's a bunch of math, but at the end of the day, the message is clear that if you do the delta call, if you do the delta hedging, if you hold the delta of the option at any point, then your portfolio change will match your portfolio change will match the price, the change in the option. And so you're perfectly hedged. That's the only message, right? So the message in terms of trading is that by holding delta shares of ST at any time in a short position, in the option, we keep our portfolio and change to be equal to the option price change at any time. So this is a perfect hedge. Okay, because by hedging, basically you try to somehow, if the option change, your portfolio change to match it. Okay. So it seems like we figure out the secret of the universe, meaning that you can hedge everything. This so in practice, this is impossible. This is not practical. Yeah, this is impossible. Okay. So in other words, actually, you can try to connect this back to those delta neutral, gamma neutral I was telling you about. Basically, it says that by keeping your portfolio delta neutral, you're almost there. You're almost perfectly hedged. The only issue is, this mathematics tells you that you have to keep continuously update your portfolio. All right. You have to keep continuously update your portfolio because at any time you have to hold delta shares of ST, a delta T change, So it's impossible from that point of view. But it's also impossible from another point of view, which is in people understand in real life, there's nothing continuous. So instead of doing things continuously, you just do it pretty close to continuous, Like you divide the interval into 10,000 steps. So instead of modifying the rebalance every, I don't know, continuously you rebalance every, let's say, hour, okay? Something like that. But it's still impossible from a second sense. So not continuously, Not possible continuously is one thing, but that's not too serious because you can always do approximation. But the second one is more serious, and that's real, is transaction cost. Okay, transaction cost. And this is like the bid-ask spread that we mentioned last time. Because you see, this delta will rise and fall, It's not always rising, it's rise and fall. So basically that means you have to sell and buy stocks. But remember, right, you try to buy low and sell high, but the market, right, will sell to you high and buy low. So every time you do a transaction, you pay a fee, right? Or you do a buy and sell, you pay a fee, and that's a transaction cost, right? The spread. Even if the spread is quite small, do you see that if you try to mimic this transaction 1,000 times, you're going to eat a lot of transaction cost? Yes. So your goal, right, as a trader is to perfectly hedge your position, right? To perfectly hedge your exposure. And the math tells you to do delta hedging. But then you figure out that if you follow that scheme, it's pretty impossible, because then you pay like tons of money just to match this. Then why not just take the risk to begin with, right? So reality, right? That's why, right, the job of a trader is hard, because yeah, there's transaction costs out there, right? And I would argue that maybe, right, part of the trader's job is to find where liquidity is, or to make liquidity. Depends on whether you're on buy side or sell side. But you try to find where liquidity is. In other words, you try to find something that is that doesn't cost you a lot of transaction cost, because I guess that's where you make money on. Okay, you still need to maintain your delta, but you must do it as cheap as possible. And of course, the math here doesn't tell us, right, what to do. The math just tells you that if you do this theoretically, like a billion times, then you're there. But reality will say, no, that's nonsense. So how to close that gap, right? It is the job of the trader, and of course I'm not part of that. But right, I just tell you that right here, the math seems fine, and the theory is built up from the PD, from the Black-Scholes PD, right, and the Black-Scholes and the Edos formula. Okay, how to make that more realistic is something, frankly speaking, right, beyond me. But those are some factors that come into considerations. Any question? All right, so I would say, right, this is the cap of the midterm. Okay, cap of midterm 1. This is everything up to here. Okay. I have 7 minutes left, right? Let me tell you, right, so where to go from here. So we spent a lot of time, right, to establish Black-Scholes formula, right, Brownian motion, that kind of thing, because it's foundational material. Okay, these are classical stuff. These are classical stuff. So now we'll take this from here to something a little bit more advanced. So from here, right, of course, there are many things, like I said at the beginning, but in immediate near future term is like this. We'll look at extension of the Black-Scholes model, extension of Black-Scholes model. And the most direct extension is to add a jump component. And that will lead us to something called the Poisson process. Okay, so it models the scenario where stock price doesn't move continuously, it has jumped. Okay, so what's the model? How do we handle the model? What's the risk neutral probability? How do we price? What's the PDE or whatever that is there? Then after we're done with that, we would look at the exotic options. Okay, exotic options, right? We'll be back to Black-Scholes model, but exotic options, right, means it's path dependent, right? So it's no longer European, like Asian, look back barrier, that kind of thing. You imagine, right, that the dynamics here will be much more complicated, because it's no longer the Brownian motion, but the maximum of the Brownian motion is involved. How do we deal with that? Okay. And there's American option, which all of you have heard about, which will involve stopping times, right? And how do we deal with stopping times in terms of pricing? And after this, right, so lots and lots of materials, right? Lots and lots of interesting materials. And after we're done with this, then we can go to foreign exchange and interest rate kind of thing. But I want to move slow. I want to kind of give you a good understanding of each of the material we do, right? rather than cover too much materials and risk losing you in the process. Okay, so for now, right, try to absorb the Black-Scholes framework very well. Let me show you one thing, right, of what's coming up next. Hold on. Right here. So this has been posted to you, right? So before we have a Brown motion path, all right? A Poisson process path is pretty mundane like this, right? It's almost the opposite of Brown motion. That it is, right, constant, but once in a while it has jump. What decides how many jumps happens here? What decides how many jump happens here is through a parameters here called lambda. The higher the lambda, the more often the jump happens. For example, let me do 0.2 here, right? And you see, notice the picture here will change by having less jump on average. You see? Run again, right? It's a random process in the sense that you see the number of jumps is random, where it jumps is random, you see? All right, and let me change lambda to be 2, okay? Whoops. You see, tons of jumps. All right. Now, then you can incorporate this jump into the Brown motion path. In other words, where this jump happens, then the stock, right? The stock has jump. And you know, you have to build it carefully, all right? And that's the topic of next class. You have to build it carefully because you see, there's some gap here that's big. Basically, the gap on the stock, right here, the Poisson process, the gap is always 1, by definition, okay? Every time it jump up 1. But the gap of the stock will be proportional to where you were at the beginning, okay? But there's some gap here, right? Correspond, and you see there's some tiny gap you cannot see because basically at that time the stock is quite small. Here to give you comparison, this is the original stock price without any jump. And you see a remarkable thing, right? With the jump, stock price end up at 3,000. This is 350, right? Obviously, this is too unrealistic, right? So we need to fine tune, right? We need to fine tune the lambda. We need to fine tune, you know, this, right? So here they're pretty close, but you see there's still a right difference, right? Of course. And so you see when you add this jump component, you have a more richer layer, right, to the stock price that you can model. Okay, so that's the topic we'll explore next. And I'll stop here today. And if you have any question, I'll answer. All right. Thanks for joining.
Yes, the problem 5 in our homework.
What's problem 5?
Problem 5, the treasury rate.
Yeah. What about Sharon?
What is the treasury rate?
I think you don't. No problem. Don't worry about it. Yeah. What about you? I was talking to Don. Yeah. What about treasury rate, Sharon? What's your question? How to use it?
Yes, how to use it. Okay.
Well, let me see. It's basically an approximation. Okay. I don't care so much. Let me look at the assignments. Homework 4. Okay. So here, right? So whoever works on this problem, you want to tell us how you do it? I want to hear what you did. Again, right, it's a very practical problem. There's not necessarily a single right way, but what you do should make sense, right? So these things you should be able to read or at least make sense out of. So if anyone did something here, can you tell us how you did it?
Professor, I selected the 3 months 3 months rate for 211.
You select the 3-month rate and 6-month rate for 211 because that's the date, right? And what do you do with the 3-month and 6-month rate?
So that's the rate. That's the rate that I have taken.
It's not quite, right? So first of all, what's the time to maturity for this option?
Yeah, so we have like close to 158 days. So I mean that would be divided by 158.
So that's like 6 months. Oh wait, 150. Wait, hold on. That's 5 months, right?
Yes.
So first of all, right, do you agree with Kashif that you have like 158 days to option expiration? I didn't look at the problem, okay, but I think that sounds right. So that would translate to roughly like 5 months, right? Let's say that 5 months. Someone say something. Let me see here. Only that much, that many days left? Yeah, there are 250 business days within a year. That's true, but there are only 80 business days left between those dates. I did not count. So how do you figure that out, Don? Because I frankly speaking, right, I don't know how many what days are business days between those times. I mean, it's very good if you look it up, but I did not count that. How do you do that? How do you get 8 business days? Fantastic. I like this. Very good. So Kashif, right? I mean, this is something that you can also look at, right? I mean, like you can have the business days of calculation. So 88 days. Then I assume, right, using this. So 211 to something, then you can calculate. Right. So what was the expiration? What was June something? I forgot already.
18th June, I guess.
June 18th? June 20th, you said? I forgot already what my homework was, but let's say do this, right? Then you got 130 days. But that definitely not, right? What was it? But anyway, so let's suppose that what Don said was correct, right? So that's going to be 88 days. Then I think that translates roughly to 3 months out. But hold on, right? That's actually also an interesting thing to see. 3 months out. So if it's 3 months out, then you would use on the 21 0.05. How about that? I mean, frankly speaking, right? 0.05, 0.06 may not make a big difference in terms of your calculation, but I would lean toward the 3 month as a use of the interest rate here, 0.05. So actually, you know what? Oh no. Sorry. My brain is not working. First of all, sorry, Don and Sherry, right? I think what Kashif says makes sense. In other words, time to maturity is time to maturity, meaning I think it's closer to 5 months. So you want to extrapolate between the two. What you use though with the 88 days is to translate that to how much interest rate you have. Does that make sense? So in other words, right, like I would say that the time to maturity is closer to 6 months, but right, remember that this is the annual rate, right? This is the annual rate. Okay, so if you want to figure out how much how much time to maturity you have left in terms of a year, that big T, then you would use what Don and Sherry were saying, 88 divided by 252. Then you will get your T. That's how I would do it. Does that make sense?
Makes sense. And what means the quoted for 340?
340.
Mm.
What 340?
Quoted.
Oh, 340 is the market price for the option.
Oh.
340 is V0. This is
Oh.
S0. This is V0. Right. I mean, I think that the calculation of interest rate, all right, is pretty tricky. So that's how I propose it. If you feel like you have a different way, then let me know. I mean, I feel this is how I would do it, right? I would go with Kashif in the 150 something as a calendar, right? Not business, but to use the what kind of interest rate span I use. But when it comes to the T, right? When it comes to the how much time left, because right, this interest rate, remember, is the annual rate, right? I need to convert it back to annual. How many years left? How much fractional year left? That would do 88 divided by 252. Does that make sense? That's how I would do it. But feel free to correct me.
How about the 2093?
That's S0.
2000.
That's S0. That's S0.
Oh, thank you.
Mm-hmm. Any other question? I mean, did anyone try your homework? Did you get close to this number? Anyone try that problem? What you got? No one tried yet?
I tried, I didn't get close to this number. I got like 0.28 or something.
0.28. Could that be because, you know, the day count that you did not use, right? Because I assume with what you did, you probably did not use 88 days, right?
Yeah. Yeah, I took the total number of days between.
Yeah, I think that might severely affect it, right? But so if you try again, see if that happens. And that, you see, Yahoo Finance definitely use Black-Scholes behind the scene. So the goal, right? I'm not trying to say you should massage your answer to match this, but I think if you do it right, you should get close to this number. So 0.28 is far. So I think that you know, again, this problem is not easy because, you know, you have to interpret, right? Which is all these things that really happen in real life. But if you interpret it right, I think you should get to this number. That's my feeling. Anyone got close to this number? No? You all get far away?
I will calculate it by my Python later. And in the midterm, if we should write code, how should we write it?
If you should write it, write what?
Code.
Oh no,
And
just
how,
not code, right? Pseudocode. You know what pseudocode means? Like say,
no.
generate a Brownian motion is a pseudocode, right? Generate a Brownian motion 10,000 times, plug that into, you know, the stock formula, the pay option call option formula, sum it up, divide by n. That's a pseudocode.
Which means that the task you ask the Python to do.
Right. You just tell me the idea that you would plug into Python. I'm not
Okay.
asking you to write down precisely what the command is. Yes.
Thank you.
Right.
Professor, how many questions would be there in the midterm?
I haven't composed it yet, so I don't know. It probably gonna be 5 or 6 problems, I would say.
Okay.
Yeah.
Thank you, Prof.
Sure. Any other questions? All right. I mean, I'm really curious on how you did a number 5, because that's a very practical question. If anyone got close, to this number, I would be very interested to know, right? It should be. I mean, that you should get close to this number. So, not that if you don't, then it's not that like it's like a serious error or anything like that. But right, we have enough tools now to get very close to Yahoo Finance number. So if we don't, then there's something about our understanding that's not quite right, I think. And I want to, at least address that, right? But yeah, there's a chance that I wrote this number down wrong too on that day. But I think I checked my quote, and I think it's right. Okay. So if you have no question, I'll let you go. I mean, feel free to sign off. And if you have a question, let me know. All right. Yeah, thank you. Thank you, Don.